All right. All right, looks like we're on the road here. So we're here at 127, and we'll do the end of chapter 8 today. There's no class for 2 weeks, and then chapter 14 here. We're skipping a couple chapters. I forget why, but for some reason I decided not to cover a couple chapters in your book. I think the stuff was too out of date or something. Let me see if I, yep. Oh yeah, it was like Solaris and stuff, I think. I forget what it was, but for some reason I decided not to cover those chapters. Yeah, that Toro Hack is a security conference in Southern California, a one-day one. So I'll be there. A couple of students are going too. I wouldn't go too far out of your way for it because there's ones in San Francisco, like B-Sides and RSA. And this, I've never been there before, but it's a one-day conference. I think kind of a small sort of local one. It might be fun, but I wouldn't expect too much. What's that? I'm going to take an airplane, but I'm putting on a workshop. I'll have fun doing that. There'll be a few talks, but I think it's quite small. One looks like one track of talks and maybe like a lockpick village or something. Not a big fair, but it could be nice. Our workshop will be fun anyway. So anyway, here we are. I'm going to do the rest of Windows, and then I'll just talk about the next Windows exploiting project I'll demonstrate it here. So we're down to the last part of this chapter 8, which is stack protection, heap overflows, and so a little bit about overflows in a data section. So we've done stack overflows on Linux and Windows, and you see how they work. And you remember, we're always turning on these compiler switches to get rid of protections. And so if you don't do that, here's some of the protections that you have. The security cookies are one of the large ones. These is also called a canary. This is where you put a value at the end of every stack frame before the stored EBP and EIP. So if you overflow a variable, you will modify that value. And when it goes to return, before it returns, it checks that value. So that's this 4-byte D word. And it goes here before the saved EBP and the saved return address. So if you overflow a variable like this name and try to change the return address, you'll also change the security cookie, and the operating system will detect that. Let me hit the mute because I think I hear funny squeaking. And I'm supposed to be able to automatically mute people, but that doesn't work. So I do it by hand when I can remember. Anyway, so the cookie, this means you need to have a random 32-bit value to put in there. If it was predictable, then you could just put in that number and overflow the stack with impunity. So Microsoft has to create a random number, and as we all know, this is very difficult for computers to do. And there are a whole series of vulnerabilities that come from insufficient random numbers. So here's what it tries to do. Counting the time interval in small units, taking the process and thread ID and performance counter and so on. And so if you can run a process on the computer, on the server, like infect it with something, and get a time measurement that's accurate, then you can learn a lot of those values. And that takes the randomness out of it. So someone did a study of the Microsoft Windows security cookie and discovered that it only has 17 bits of randomness. Now 10 bits, 2 to the 10 is 1,000, 2 to the 20 is 1,000,000. So that's somewhere between 1,000 and 1,000,000. So that's pretty good, but not that great, because say if I have to try 1,000,000 times to get in, I might be able to try it 1,000,000 times on a computer. That might not be beyond the bounds of possibility. So this would be 131,000 is what you'd have to try with the Microsoft Windows Defense, which is of some value anyway. And here's how it works. And I'm sure got used to this from CTFs. Every time you analyze code in a debugger, you see this. At the start, it moves the security cookie from storage into EAX and then stores it on the stack. And then at the pro epilogue, when you're returning, it checks the cookie on the way back. And if the cookie is modified, it does not return. It just stops and sends up an error message. So I've gotten used to seeing this in the debugger, and in a lot of CTF problems, you evade it for various reasons. Of course, if you want to get around this, you have to either find some way to read that value so you know it, or find some way to change that value and change the other copy of it, or some way to jump over some of this code. But there are ways around it. Here's what security check cookie does. It compares the data it found on the stack to the authoritative copy in the data section. So that's how it works. All right. There's another defense, which is just to rearrange the order of the parameters. Before the GS flag in Visual Studio, it came about in 2003, it would just put variables in the order the programmer defined them in. And that, now it moves them, so all the arrays go to the end. And the idea is, if you have an array at the start, then you can overflow everything, get down here. If you move the arrays down to the end, then there are less things for me to hit. It decreases the damage of buffer overflows. Now, this is not protecting you from hitting the EIP. This is protecting you from overwriting another variable, which is the kind we had much earlier in this class around Project 2. We had the kind of Stack Overflow where you leak from one variable into the next. And I said that is not very common, but one thing about it is it's very hard to stop because you don't hit the cookie, you don't know what happened. I mean, it's very hard to tell. If I was to write like 30 bytes in this name variable and change part of this password variable, it would be very hard to know that that was not acting as intended. I'm in the stored variables, I'm writing stuff. You could even write code that deliberately mixes these together. That's just what you're encouraged to do in C. Be brilliant and just use the same pointer to mean two things because you have it all in your control. You know, I don't really know how automatic defense could catch that kind of thing and stop it. Anyway, so that's the game. So when you overwrite parameters, if you start overwriting the buffer down here, you'll be changing, you're trying to get down to these other parameters down here and hit the save return address. So that's the issue. If you change the cookie, by the way, in this case, even if you change parameters, which are on the other side of the stack pointer, you might find something that is used before the cookie is checked. So you might be able to get somewhere by overflowing one variable into another. All right. Another thing you could do, if you were to override a parameter and that parameter was used in a write operation, you might be able to get an arbitrary write, the way we've done before with, say, the heap overflows. You were able to get an arbitrary write, and then you could do something like overwrite the authoritative copy of the cookie. Now it's write to a location. So another thing you could do is overwrite the security handler and let the cookie check fail and overwrite the code it goes to when it fails, which is probably an exception. These are ways to get around it. All right, so then there's heap overflows. We've done the heap overflows in Linux. In Windows, they are much more complicated, but the general principle remains the same. If you have code, any kind of program that handles large chunks of data, but it doesn't need to keep them around forever, then you use the heap for things like a network stack where you have data coming in, you process some portion of it, and then throw it away. So you'll be allocating room on the heap to store this while you process it, and then freeing that space to handle the next chunk of data that comes from the network. Every process on Windows 32 has its own heap. By default, it is created and called the process heap, and you can just use that if you want, and that's what most of the API calls do. But you can also break it up into chunks, into subheaps if you want to. And so this is the code that returns the pointer from the process environment block to the default heap, the process heap, and that's all the Windows API calls do, just to keep them simple. They use the default heap. But you can make other heaps by cutting out chunks of the default heap with the heap create function. That will create another heap to use in your code. So you have the default heap here in the process environment block, and then you can have an array of further heaps. A heap down here, a dynamic heap created there, another dynamic heap. So it is possible to segment it into other heaps. So the heap allocate gets a chunk of memory on the heap to put data in, and this is a local alloc and global alloc are leftover ones from 16-bit Windows. And when you're done with it, you call heap free. So that's the same process in Linux as alloc and free. You alloc some space, you store data in it. When you're done, you free it to make that space available next time. And just as before, the free is the dangerous part. So remember, the stack grows downward towards 0, the heap grows upward. It has a list. It is a doubly linked list where each chunk of heap data points to the next data and the previous data. And that means when you free a chunk of heap, you create this operation where this is now made available in the middle, and the pointer at this end has to be updated to point to this end, and the pointer on the right has to be updated to point to the left. And that means you have a write operation over here on the right that is writing data from this area to an address specified in this area. So if you're able to overwrite the data on the heap and leak into here, you get it right where you control both parts of it. You control the address it's writing to, and you control the data that's written to that address. And that's what you typically find, and we've done it in Linux. You get a heap overflow, you get a write where you control both ends. And once you have a write, you can take over the machine by just writing some kind of address that's used, like a stored EIP or an exception handler address or a library C call, something of that type. So it is, in fact, much more to it in Windows. There's these things called look-aside lists. There's a bunch of heap defragmentation routines for efficiency on the heap. There's a lot of complicated details you can get into, but the general principle is the same. You overwrite a heap, you get into the control portion in the next chunk, and when you free it, that turns into a write you can control. Yeah.
What are those lists?
They are things added to Microsoft heaps that make them more efficient. And there is a lot of attention in Microsoft heaps paying attention to the largest contiguous space and defragmenting the heap to combine it to make another usable space. And these are all used for that. And I don't know any more details than that. I've read a few blogs about them, and it gets very complicated.
Also, the appendage or the suffix .list.
Yeah, there is a, well, I don't know about I'm not sure. There isn't a list file. I know there's plist files in Mac, and I think there are also list files in Windows, but I'm not sure what they do. Yeah. All right. So anyway, once you have an arbitrary write, like say here's things you could do. You could overwrite the pointer to the exception handler and then trigger an exception. You could overwrite the unhandled exception filter so that it'll go there when it fails to handle an exception. Or you can overwrite any pointer in the process environment block. Yeah. Yeah, the frame-based exception handler is code you put in specially, and if there is no such thing, or if it does not handle that type of exception, then it goes to the unhandled exception. And so either one of those give you an opportunity to take over control. And the process environment block has more things. There's a thing called enter critical section. You can point, and this is called whenever a process exits. So it's, again, a place you can overwrite and take over control of the machine. And it's fixed for all the versions of Windows NT. So that's pretty good. You don't have to hunt for it. So Windows 2003 doesn't use those pointers, but there are other functions that call pointers we can control. So there are API calls that do use pointers you can find, and that's what you do. You find some pointer that gives you control of the machine and that you can locate, that is not jumping around in memory. Vectored exception handling was something added in Windows XP, and this stores information about handlers on the heap. So it creates another vulnerability. You can, and here's the one where you go to the unhandled exception filter. An application can set this value here, and the way you do all this, which we've definitely done in the other classes, is you use WinDebug, and you can debug the Windows kernel, and you can list all the API calls. We do it in the malware analysis class, and you can just look at the code. So this is how you, this is why everything in Windows is not open source, but it might as well be, really, because you can totally see the code and figure out how it works, and that's how all this stuff works. You can find the this API call that sets the unhandled exception filter, and you can just disassemble the code with WinDebug to find out where it is. And now you have something you can overwrite to take over the machine. If you overflow things on the heap, you have, of course, corrupted the heap. You've altered the pointers for some other purpose, so now the pointers don't point to the next chunk. So you will probably end up with an access violation, and so you probably want to repair the heap. And the simplest thing to do is to just erase all the other data from the heap. So it contains only one chunk, the chunk you're using, and that will at least be a valid heap. It will have other consequences by erasing other data the program might expect to see, but that way it'll probably not cause an exception to just continue running the program. If you mess with an exception handler, you have to be sure and replace it. If you don't put it back to a valid value, then if your exploit has an exception, and shellcode often has exceptions. We talked about this right at the beginning. If you have shellcode, shellcode has no error handling. So if you try to do something like connect to an IP address and you don't get a reply from that IP address, it will cause an exception. So shellcode often causes exceptions, so you don't want to have a broken exception handler at that point, or you'll get stuck in an endless loop. All right, And then there's Comm Objects. We've talked about these before. The Comm Objects are objects that are created upon request from another program. And this is, of course, very dangerous. This is one form of remote procedure call. So these objects are created on the heap, and they're created with an interface which connects them to another program, and that goes to a thing called a vtable that points to a bunch of methods. So there's a whole bunch of pointers created on the heap that are used as addresses to call code. So that's just asking for it. And if you can overflow into the next object's vtable, you can overwrite these pointers, and when that function is called, you have control of the machine. So it's handy. A whole bunch of pointers used for calls. Another thing is, this is also true of Windows ActiveX controls, although you don't hear that much about them anymore, but Comm is still an integral part of Windows, unlike ActiveX. And it turns out there are a lot of things where Microsoft doesn't patch things very well. There are thousands of Comm objects in your Windows machine, and many of them are known to be vulnerable. And when they're known to be vulnerable, they're not actually removed from the operating system. They're just added to a list of kill bit objects to ignore. And it is pretty easy to circumvent that kill bit and execute the ones that are known to be vulnerable. So it is kind of crazy. You can load a program into your Windows machine and see these Comm objects, and that's what I've got here. It's Ole Comm Object Viewer. You can run your Windows and just see there are a lot of them, and a lot of them are known to be vulnerable. So this is a pretty rich field to find attacks. Well, now you can examine them. They all go to DIL files. I mean, you have to read the assembly code and figure it out, or you have to find one with a known vulnerability. And there's that technique in a link. I don't know the details to turn off the kill bit.
But what they put in the queue is they disable them.
Right. These are disabled, but you can re-enable them. And it's probably just as simple as an API call, but I'm not quite sure how it works. I remember that's true of almost all Windows defenses. There is an API call to just turn it off. So, yeah. So, I mean, that's why, in a way, it has to be that way. The computer has some way to do anything. So there is some function to turn the defenses off. So all these defenses really do is stop old malware that didn't know about it. There's always, within a year or two, new attacks that figure out how to turn off that defense. That's just the way it is.
Is there a way that you can know which software uses which comms?
I don't know. The question is whether you can tell what software is using what comm. I imagine there is, but I don't know. I would think if you use PE Viewer and Dependency Walker, that would be my first step. We got this in malware analysis class. PE Viewer lets you see every library call that's used, and Dependency Walker lets you see all the code that's being used, and I would think that would be a good place to start. But I don't think it'll get you down to the level of comm. Another thing you could do is run it and then look at it in Process Explorer, because Process Explorer lets you go all the way down to the handles. So I bet you could do it with Process Explorer. I do not think it's in the Immunity Debugger, but I'm not sure. Let me just, it's a very interesting question. Let me just see if Immunity can do it. Can it see Comm Objects? I don't think so, but let's see. How to find memory objects using, yeah, you put a breakpoint at the received function. There are some ways to hunt for them here, but it isn't terribly simple. But there are some blogs very recently on how to do it. So I don't know the answer. But he says Control G, yeah, I'm not sure. Not a simple way that I know of. All right, and then you can overflow in the data section. If you have global variables, here we've got a global variable defined outside any routine. So it's a buffer 32, and then there's a couple of other things down here that look like pointers. So if you can overflow that buffer, you can overflow other global variables. And these are all in the data section, not in the text section, not in the heap, not on the stack. The data section is where global variables live. And of course, here you've got the kind of overflow we've used before from one variable into another. So what good it is just depends on what the other variable is used for. But if one of them is used for a pointer to a routine, then that's an obvious way to take over the machine. All right, you could overflow the buffers in the thread environment block in principle, but there were no examples of this exploit. It's just something that might happen. And I think that's it for these slides. So I got some Kahoots about that, and then I just want to talk about one of the projects. Let's get my Kahoots up. I think they're here. Nope, that's something else. Let's see if I can get my Kahoots. There we go. And this is 127. It's in shared Kahoots. There we are. Okay. All right. That's a good name, Pop Pop Tip. All right, I'll give it another 10 seconds. I've noticed we have Kahoot abstainers. There's like 11 people online and like 8 in the room, but only 10 players. Conscientious objectors against the Kahoots. Anyway, all right, so. All right. So which one is a canary? That's the cookie. Good, okay. Which one is used by most Windows API functions? Okay, they use the process heap, the default heap. They don't create dynamic heaps typically. All right. Which one uses killbits? Okay, those are the Comm Objects. All right, which API call is most likely to be exploitable? Okay, it's when you free a chunk is when you create something that's very likely to turn into a write you can control. All right, so which one of these is created when needed by another program? Okay, those are the Comm Objects again. So the winners, Bill M. and Crystal Corp, I think I know who that is. And Al, you probably have to tell me who they are. All right, and let me just talk about the projects. I've got, here we are with the projects. There's one of these I just updated a little bit today, a couple of them actually, but the one I want to talk about is this one here, the Easy RM to MP3 converter. So let me, here's my Windows machine, and I think I need my Kali machine also. So let me arrange things on my screen a little. All right, and I'm using my Kali 2018 machine, although it doesn't really matter. I'm just using it to create code. So it doesn't matter if it's 32 or 64-bit or what version it is. Since I don't have any VMware tools that actually work properly on my Mac, I have to use SSH to get to the command line, and I have to use a FTP client to move files in and out. I've gotten used to this. It's actually good to have it because it means I could just as well be using a cloud server for that Linux machine, and it would be the same process. So now I can move files in and out. So let me get my vulnerable application. This vulnerable application is here. Okay, this is something else. Let me just try and clear up junk off my screen. That was another project with ROP chains. We'll do that one next time. But the one for today is a viewer. And I think it was on my desktop. Let me see if I can figure out what I did with it. Let's try documents. Easy.zip. And I thought I already installed it. Let's see, is it in the, here, maybe easy? Yeah, easy RM to MP3 converter. Now this is a type of exploit that you'll see fairly commonly with things like zip utilities and PDF readers. This is something that converts one format to another, so it takes in a file. So you can load files here, and you can also load playlists. And it turns out that the particular vulnerability we have here is in the playlist. So I've got examples of a file here. Let me just show you how I made that file. If you go here, the first thing I did was do the fuzzing. So easy fuzzing. Oops. Fuzz 1. Okay. So what this does, this just prints 10,000 days. And you just put that in a file ending with the file extension of M3U. So that file just contains 10,000 days, and this one contains 20,000 days, and that one contains 30,000 days. That's all they are. If I do ls-l, easy star, you can see 30,000, 20,000, 20,000, that's what they are. So if you try opening those in this program, I can load from documents a playlist file, and here's the fuzz one. So when I load that, it loads. It says failure in loading file, and it prints a message, but it did not crash. So that's not a crash yet. So you got to try a longer file. So you try 20,000. And again, it doesn't crash. But when you do 30,000, it crashes. So that's a crash, and that's what you want. This is your first step. And it shows me, by the way, that it's a stack-based crash, and it shows me that the offset is 41, 41, 41, 41. So I'm not quite sure what the exception offset is, but I think it's something like EBP. I'm apparently able to overflow something and overwrite some registers. So this is promising. And in order to find out more about what's happening, of course, you've got to use a debugger. So let's start up Immunity and run that thing inside Immunity. I'm going to maximize the CPU window to get the normal look, and I'll run it here. So the program is launched, but it stops. I have to run it here, and when I do, it'll pop up the box, and now I can feed in data. It asks you some kind of preferences all the time. I just click OK because the default preferences are fine. And now I load the thing that is going to crash, which is the 30,000 one. And now it crashes. And this is actually very promising because you can see at the bottom here, access violation when executing 41, 41, 41, 41. So this is the most friendly kind of crash. Some of those A's ended up in the EIP. So I don't have to hunt too far. And as I think I mentioned before, but I'll mention again, if you click around and mess around, this thing will go away, this box. If that box ever vanishes on you, before you get a chance to read it, you can go to logs, and it's all in the logs. Access violation when executing 4141. So now I know that some of those A's ended up in the EIP. So now the next thing is just to make a non-repeating pattern. There's a Metasploit module that does this. I always just write my own because it seems simple enough. But you need some kind of non-repeating pattern of text. So I made this one where I go from 41 to 5A out here, which are letters. And then I go from 0 to 10 and 0 to 10. So I print a letter and then a 2-digit number. And then I printed the letter twice and then a 2-digit number. So the pattern I get is like this: VV77, VV78, VV79, and so And I went through 25 letters from A to Y. So that whole mess is here. And I just wrote a code to add 20,000 days first, because I know 20,000 did not crash it. So it seems most likely that the buffer was overflowed by the last 10,000. So I put 20,000 days, and then I put 10,000 worth of those patterns. So the data that comes out is like this: AA0000102 to AA99 down to YY. So that's the pattern, and that's what I've got in this file here. I can go back to here. I can close this log file. I don't need that anymore. And I can do debug restart to reload the program. So now it's back in the clean condition before the crash. I run it. I set the preferences to default, and then load that file again, which is a playlist. And it is this one here, EIP1. So when I run that, it's now got an access violation when executing. And the thing it executed was 39, 50, 50, 32. And this is in hex, so it's 9 PP2. The 50 is P, I think. Yeah, P is 50. You can see it up here in hex, which is the second column. 50 is P, and the numbers you can just read right off, because 30 is 0, 31 is 1, 32 is 2. So that is this one. It is 2PP9 or 9PP2. Remember, it's backwards. So 9PP2 is a 9 on the right, 2 P's and a 2 there. So where that is here in that non-repeating list. So it is, I can just count the letters, and each one of these rows has 400 entries. And then I can count across to here and add it up. So what I did here was add it up for that one. If you're running it on a client-side version of Windows, like Windows 7 or Windows 10, it will crash here at 2PP2. If you're running it on the 2008 server, it crashes 12 bytes earlier. So you have to customize it to your system. It's not the same on every version of Windows. But I used this before, previous semesters, I used Windows 10 32-bit or Windows 7 32-bit, and I got this. When I did it this morning on server 2008, it was here, so it's 12 bytes earlier. So wherever it is on your system, find it, and then you know what number to put here. So this is the code that targets the EIP precisely. 20,000 plus 15 complete rows plus 22 groups of 4 plus 3 is how you get to it. And in my case, you then have to subtract 12. So here's the code I actually used. This is easy EIP2. Okay, this is what worked on my Windows Server 2008 box. 20,000, 15 times 400, 22 times 403, and then minus 12. That's how much padding you need. Then you put in B, C, D, E. Then you put in enough Fs to keep the total length at 30,000, because as I said before, you always want to keep the total length of your exploit the same to make sure that you're having the same crash and not hitting a different vulnerable instruction. So that's the game here. And that one is EZM EIP2, which I've already transferred to the Windows machine. And so if I restart my vulnerable program with debug restart, yes, and then run it here, I can load, accept the default preferences and load the playlist of EIP2, and you see it worked because I hit 42, 43, 44, 45. That's B, C, D, E. So now I control the EIP. All right, now that would be enough if it were not for address space layout randomization. But because of address space layout randomization, I do not know what number to put in there. I can't find my code. So we have to use return-oriented programming to overcome that. And that's the game here. So now I can control the EIP. I just need to figure out what to put in there. Now, the first thing is to find out what's at the stack. So here, you can see right here in the debugger, up here on the right, here's the ESP, and it points to FFFF. And the way I built this was I had A's, then I had B, C, D, E, then I have F's. So some of the code I injected is over here at the ESP. And that's good because jump ESP is a common instruction. So I might wonder what part of the stack I'm pointing to, so I can left click on this and then right click and follow in dump. That's one way. So you see here are the F's, and if I scroll up a bit, you'll see here's the A's, there's the B, C, D, E. Right there, it's right at the start of the F's. So I can just put my exploit right in where those F's are, and I can easily get there if I find a jump ESP. And we've done this before. To find a jump ESP, you use Mona. Now, the next, you can find a vulnerable module with Mona modules. You want to find a module that doesn't move. So we need to find, now if everything had address space layout randomization, then we would not be able to find anything to put in there that would work all the time. And we'd have to do something more drastic like keep spraying. But in this case, we can find modules that don't move. So let's start with Mona modules and put that here. Whoops, not there, but here, okay, there. All right, so there's the modules. And as we've done before, the cool thing about Mona modules is it tells you what defenses are turned on for each module. So let me get, there we are. This tells me whether we have safe SEH, ASLR, NX compatibility. This is data execution prevention. If this is on, then we won't be able to execute code we inject. If this is on, the code will be jumping all over the place. And this has to do with the structured exception handler, which is not the exploit we're using today, so we don't really care if that's on or off. So we can see various modules here. Yeah?
Is this a Windows app or this moment?
Is it a Windows, what?
Is it like just combined with Windows operating system, this moment?
That's a good question. I've never seen Mona used for anything other than Windows. I do not know.
Because my question is,
yeah.
My real question is because this kind of tells you what part, like you said, we're in execute code.
Yeah.
Do we have something similar for that in Linux?
I'm sure there is, but I don't know what it is. That's a very good question. The question is, what would you use to do this job in Linux?
Yeah, exactly.
And I don't know the answer, but it would. I'm sure there is something, actually, and it would be a good thing to add to this course. I'll take a look for it. If you come across something, let me know. That would be good to add to the project. It is. And it might run the same, but I know the defenses are different, so I couldn't, the exact same code would not give you the right answer on Linux, but there could be some version. There must be some comparable program on Linux. It's a very good point. I do not know what it is. I do know a lot of Linux code does not use dynamic libraries, but now more of them do. So it is a good question, especially on modern versions of Linux. The defenses are comparable, and so therefore the attack surface will need to be comparable. Yeah.
The first one is, what if you cannot find the first one? Like all of the models are true.
Yes, if all the modules are moving, then you will have to find some way. There are other ways to attack it. And the one we're going to use later is heap spraying. What you do is you make an exploit with a very large NOP sled, like 10,000 bytes, and then you fill all of memory with it, thousands of copies of it, and then you just jump at random. And you have a high chance of hitting it. That's why you don't need to know where anything is. That's one attack. The other attack would be to somehow turn it off. But the heap spraying is the most common one, and you do that in a web page in JavaScript. You just fill all of memory with your attack. And then you jump typically to an address like 08080808. You just pick an arbitrary address and jump.
And another one is why some of the for that ASL one, why some of them are false and some of them true?
That is
the ASL turn on already.
Yes. What happens is when Microsoft adds a defense like this to Windows, they are not able to do it to everything. Some of the internal modules have hard-coded addresses. So this is the way it always is. Old code doesn't know about this. So Microsoft typically does not turn on the defense everywhere. They turn it on some places, and other places it's too inconvenient, so they leave it off. So
even in one program, in one software, some of them.
Yes, and also if you run any legacy code, which we're doing here, this Bowne server, that won't have it turned on. So this is why this is a big issue for Microsoft, and this is why they've actually gotten so far as to start pushing out updates. People keep running old stuff, and Microsoft has vigorously supported that all along for business reasons, but if you run anything old, you're vulnerable. So forcing you to use the new version of everything is always more secure, but people are not willing to put up with that. And the problem is it extends not just to the software you wrote, but to the kernel and the device drivers and everything else. You really can't have only new stuff on your machine. You have a lot of old code. And some of it comes from a time before this, so it's not ready for ASLR. That's why, that's the general answer. The specific answer as to why Microsoft doesn't do it, I don't really know. And it may not even be public information. Those of us on the outside try to guess what Microsoft is thinking. And there are some things Microsoft does that just remain utterly imponderable, like null sessions. I've never heard anyone explain why that happened. That makes no sense at all. It must have made sense at some point to do that, but it just looks utterly stupid and indefensible now. So anyway, we're looking for something to exploit. So we want to find one with ASLR false and rebase false, but the only one like that, because then you know where it is. But that one, the only one is the converter itself. And the problem with the converter itself is that it's got zeros in the address. So let's see, I should be able to find that one. Perhaps in my live one here. MP3 converter itself should be at 400,000. That's where it usually is. And let me see if I can find it. I don't know how to scroll to the right on this thing.
Don't you have a command to look for all the false one later on in your lab file?
A command to look for
All the false.
down here. Yeah, this will look for other, command to look for what?
All the false listings.
All the fours? Oh,
yeah.
There might be. Anyway, I think this is MSRM filter. Anyway, I'm not going to struggle with it. But the, anyway, this module had a null byte in the address. So the next thing was to set for rebase equal true and ASLR equals false, because this will see, rebase means if another module is using that address, it will move. But that often does not happen. ASLR means it will always move. So ASLR is more important. So we can use, yeah, that's good. Here's 3 comparing comparable runs. And so keeping only the modules with ASLR equals false. Yeah, what I did here, I think I just filtered it in Notepad afterwards. I don't think I found a command that did that. I think I just trimmed the output. So here is an example. And the one I'm planning to use, here's the MP3 converter itself. And you can see the problem with that. That's what I thought. Your main program always runs at 400,000. That's the virtual address. And 400,000 is no good because it's got null bytes in the start. Almost all the addresses that are available in here are going to have zeros in them. So we can't use those. So the one we're going to use is MSRM filter 03. And so that is filter 03 right on top. Okay, that's the first one all 3 times. So I ran it 3 times. And you can see here it is starting at 100 million, 100 million, 100 million every time. So it's not moving. It would only move if some other process used that address. And since I'm not launching a lot of other software on my machine, it's not happening. So if I assume that my client doesn't use that address, this is relatively dependable. So now the question is, can I find a jump ESP in that module? And this command will do it. And when I do, I find one of them here at this address, 1001B058, and that address doesn't have any null bytes in it. So as long as none of these is a forbidden byte, I should be okay. And that's the game. So now the next thing is to test code execution. I think I'll just talk about the rest of this because this is all stuff we've done before. So to test code execution, you put in CCs. You put in an op sled and you put in some CCs here because it will either hit the NOP sled and stop, or it will slide through the NOP sled and hit the CC. So we can tell whether we have executable code. So you put the NOP sled at 90 here, and you know that the stack is going to show it. So here, let me do this one live. This is worth seeing. This is EZM EIP4, and I should demonstrate the whole process here in case that's not clear. EZM EIP4. So here's the code. Now what you do is save that. And by the way, I'm off by 12 because this code was from my instructions, and that was for Windows 7. So I have to subtract 12 for it to work on my operating system. I see a comment coming in. Let's see. I can get them to come up here. Okay, I had the problem on some homework where it stopped at the NOP sled. Yes, if it stops on the NOP sled, that means that data execution prevention is on. And that means you cannot run any code you injected. So what you have to do then is you have to turn off DEP. And that is in one of the projects. There is a Mona module that will create a series of addresses to use to reuse existing code to turn off DEP. I think it's in the project called Defeating DEP with ROP. So it can be done, but it is pretty complicated. And you have to put in a whole series of addresses. But that's what it means. If you can't execute a NOP, the only thing that can cause that is data execution prevention. That's why this is the logical test. This will tell us how many defenses we have to overcome. Yes, you can turn it off, but in advanced system properties for yourself, for testing purposes. But if you want to turn it off on a remote server, you have to find an exploit to turn it off, and that you do with Mona. Mona will build the series of addresses to feed in that will chain together instructions that are already there into code that turns off DEP. So now does it come up? Let me pause this demonstration long enough to point you to that project because it is really important and it is covered. So let's find it here. This one here, project 11, the next one. In project 11, we will defeat DEP. They'll do that next time. But this is where I'll be find Mona. Okay. You use Mona down here, and this Mona ROP, this is what does it. This creates a ROP gadget, which is a whole series of instructions to execute. And you'll see them here. All these instructions, all these addresses have a couple of assembly language instructions, one after the other, and those are enough to add up to enough to turn off DEP. So it hunts and chains them together. So you have no code you execute. All you do is feed in a bunch of addresses, and the addresses go to code. This is how it works. That will create the NOP chain.
How do they chain it up? How do they chain it up together? Do they really use the code?
Because you were able to control EIP. You have to have this kind of exploit. Remember, we can control EIP. We can put an address in there and it will go here and execute code. So you jump to the end of a routine. So it does a couple of instructions and then does a return. And when it returns, it comes back and executes the next address that I put there. So I just put a whole series of addresses in.
So you look for those people.
Yes. And that's the hard part. That's what Mona does, which is awesome. It hunts through all the routines and it finds little pieces it can paste together, like building a ransom note by cutting words out of a newspaper. It finds little pieces which patch together what you need. And then it just gives you all those addresses. And so you just put all those addresses in on the stack and it will just execute them one by one. It's almost insanely complicated, but Mona does all the work. And it used to take like half an hour to do it. Now it's getting pretty fast. It's very cute. Yeah, Mona is doing a really big job. And Python is awesome. You can use an interpreted languages for that. Anyway, so what we're at now is this one. And so I should mode it. Plus X, I'll just do easy star. Yeah, plus X, thank you, not S. X is, yeah, X is different. Okay, now I run that. Easy EIP4, and I put that in easy EIP4.m3u. And now to make sure I haven't fouled up, I want to check the length. Here's my stuff. And 30,001 is what I want. And it looks like it's 30,001, so that's good. So I'm going to move it to my machine. Now to do that, because I don't have VMware tools that work on the Mac. I need to do it this way. I need to get to my desktop because I can't copy into a virtual machine from any folder other than a desktop. There. So here I have my FTP client. And I refresh this. There's my thing, Easy EIP4. I put it here. Now I can put it in my Windows machine. And here I can put it in the documents. I just need to somehow make it all fit on the screen. Okay, there, that's gonna work like that. Okay, now I can open up documents. Okay, now this here goes in here. That's why I've been skipping a lot of, that's why I had a bunch of these set up before because the process is kind of clumsy. But now I have that file in there and let's see if it works. I go back to my debugger. I restart the program. Okay, I run the program. Now I try to load, get rid of this thing, load from documents, a playlist file, and it's this one, Easy EIP4. Okay, and now it worked because see what I got here is int3 command. If I scroll up, you can see that it worked. It executed some of the NOPs and it hit the int3. If DEP was turned on, it would have stopped up here at a NOP. And it did all the NOPs and it executed the int3 command and then stopped, and that's what I wanted. So now I know I can execute code that I put on the stack, and I found a jump ESP that doesn't move, so I can put in an address that will get there. So now all I have to do is put a real shellcode here and I win. So I'm nearly done, and this is all pretty much stuff we've done before. So let me go back to here. So now that I've done that, now that I know I can execute code, all I have to do is make code. So I tested for bad characters by changing my code, and here I cheated. I don't even have to test for bad characters because I can, since I have a lot of room, remember I have 10,000 bytes to put on the stack. So I can make an exploit that is big. If you don't care how big the exploit is, you could just limit yourself to a very limited alphabet. And what I did here is just limit myself to alphanumeric values. I'm just going to assume that I can use letters and numbers because I probably can, and I won't use any funny characters at all. And that will make the exploit fairly big. It will make it, the size should be down here someplace, 710. Remember, before we were able to open a listening shell with like 200 bytes. If I'm willing to just use 700 bytes, I can just restrict myself to alphanumeric, and then I can skip that issue of bad characters, probably. So this is the command that does that. And by the way, as we've done before, I used exit func equals thread to make the attack work better. Otherwise, it tends to hang up on you when you connect over the network. So this creates an attack file with a bunch of binary to use, and I can just put that in. I put in all the same stuff I had before. I put that in on the stack. I know what address to put on the stack, the same address I've been using, that jumps to jump ESP, and that creates the exploit that takes over the machine. And here I used a remote shell, which is another habit you should have. I mentioned long ago, the attacks we've been using are really pretty worthless because they open a listening port on the server, and anybody with a firewall will not fall for that because I'm listening on some unexpected ports, and they should not allow any traffic to come in to an unexpected port. So what is much better is to do this. You start a listener on your target machine. Here I'm listening on port 443, which is good because almost everybody lets you make outgoing connections to remote 443. And then in my attack, I have to put in the address of my command and control server here and that port number. So when I run it, it will phone home to me. This is much better. This will stop anybody that has a normal firewall. The only people that will be safe from this, which should include you, by the way, if you're managing a server, you should not let your server make an outgoing connection to a website. People shouldn't be opening Internet Explorer and browsing the web from your server. You can block this too, but many people don't think of that. And especially in this case, we're exploiting an MP3 converter that's probably running on end user's device. So that device almost certainly is browsing the web. But anyway, I saw a chat comment come in. Let's see what people are saying. Okay, it means you can't execute code you put on the stack. Yeah, what I used in this case was Windows Server 2008. And I also did it on Windows 7 and Windows 10. It works on any of them. Yeah, okay. And you can go, as we were talking about, if you go into Advanced System Properties, you can turn on DEP. And then that would stop this exploit from working. All right, good. Those are good questions. Yeah.
For this exploit, do you have to stick with the specific point?
Yes, you do. You have to hear, this is what your server is going to be listening at, and Metasploit requires you to specify its IP address and its port number. Real malware, like Configure, has a generator and tries thousands of addresses hunting for the server. And you could do that, but Metasploit just has one fixed point.
You're doing reverse TCP, right?
Yes, this is a reverse TCP shell, that's right. And there are a few other kinds of shells too. Let me see what's coming up in the chat, though. There may be more about these defenses. Yeah, Dan, oh, he's asking Dan. Okay, yeah, see if Dan has more. Dan was, oh, he's asking what version Dan was using when he had it stopped. Yeah.
Does Linux have the immunity debugger?
I don't think Immunity runs on Linux, but you use GDB. There are graphical debuggers for Linux that basically run on top of GDB. I don't find them very useful, but some people do. And there are some exploit environments like
GDB allow you to run Python code, right?
I do not know if GDB supports Python code easily.
So inside GDB, you can run Python.
Oh, you can execute shell commands from GDB, absolutely. And I have, in fact, automated GDB. You
run it before. Inside GDB, you run the command.
You can, yeah.
Python code.
Well, that just went out to the shell and ran it. I'm not sure about running it inside GDB. You can execute shell commands from inside GDB, but it's just a shortcut. It's just executing command outside GDB. But you can also take input. Yeah. Yeah, but I don't know a way to add extension like Mona. But I mean, this guy used 2008. Yeah, turning off DEP would make your life easier, Dan. Yeah, turning off DEP would stop that particular problem from happening. If you want to exploit something with DEP, then you do Project 11. We can take over machines even with DEP turned on. Yeah. Did you allow your Bowne server in the register to execute code from the stack? Yeah, the trick is explained in the previous course. Okay, fair enough. Good. Looks like I think they've got those comments. Any other comments? I think that's it for this one, and that's enough for one day. There'll be no class for 2 weeks. We'll pick up in 3 weeks. Now I'm going to go back upstairs and see if anybody needs help up there, unless anything else is happening down here. All right, I'm going to stop the share. I'll see you folks in a couple of weeks. All right. End meeting. Okay.